We have covered so far in these lectures topics such as dimensions, errors and their treatment, and vectors, their addition, their multiplication and so on. Today, we intend to concentrate on graphs, the distance time graph, the velocity time graph and the acceleration time graph. We shall also see how a good graph should be drawn. So, we start with displacement. You know already the displacement is the difference between the final position vector of a body and the initial position vector of a body. I will show you here how we get the displacement. This is the initial position vector, this is the final position vector and this is the displacement vector b minus vector a. We shall denote displacement by capital S with an arrow on it, whereas the distance covered we shall show by small s. You know already that average speed is defined as the total distance covered divided by the total time taken. Now, the distance covered would depend upon the path taken as shown in this diagram. We go from A to B and we take a very meandering path, and if we measure the length along this path, that would be the distance travelled, whereas from the direct arrow from A to B shows the displacement, and the displacement from A to B is the positive displacement, and if we take displacement from B to A, it can be negative displacement. So, displacement can be positive as well as negative, whereas the distance covered is always positive. Here I show you this, that you go from A to B and go from B to A, your distance covered would be twice the distance between A and B, that is 2 L, whereas the displacement would be 0, because you started from A and you have come back to the point A. You know already that velocity is equal to the slope of the displacement time graph. This we did in the last lecture. Now, the slope of a linear graph is constant, it is the same everywhere. So, if the graph between displacement and time is linear, then the velocity is uniform. That means, the slope is the same everywhere. You can see how we measure the slope. We measure the slope by taking at a certain time the displacement and divided by the time taken. That is how we find the slope, and if the graph is linear, the slope is constant and therefore, the velocity is uniform. However, if the graph is not linear as shown here, then the velocity at a point like P, for example, is found by the slope at P, that is delta S by delta t. At the point Q, the slope is found again by delta S by delta t, and you can see that the slopes at these 2 points are different. This means that the velocity is changing, it is not constant. If the velocity is not constant, then we have to define what is known as instantaneous velocity at a point, and that is defined as vector v is equal to the differentiation of vector s, that is d s by d t. Just like the velocity, the instantaneous speed is also defined as d s by d t. Remember, the small s is for distance and capital S with an arrow on it is the displacement. And now, we have to establish a relationship between the speed and velocity. How do we do that? We take the point moving on a curve as shown here, and we take 2 points which are very short distance away. In that short distance, the displacement would be equal to the distance covered, and therefore, the velocity would be equal to the magnitude of the speed would be equal to the velocity vector, the magnitude of the velocity vector. So, the speed is just the magnitude of the instantaneous velocity. Just like velocity, instantaneous speed can be defined as ds by dt. Remember that small s denotes the distance covered, whereas capital S with an arrow on it shows the displacement. How do we relate these two quantities, the instantaneous velocity and speed? Let us take the body moving on a curve, and we take 2 points very short time away from A to B. The distance is covered in a very short time dt. Since the distance is very short, the displacement would be equal to the distance covered, and therefore, if we now find the speed, it would be equal to the magnitude of the velocity. That is, ds by dt would be equal to the magnitude of d by dt of s vector, and this means that the speed is just the magnitude of the instantaneous velocity. How do we plot a good graph? It is a convention to plot the independent variable along the x axis and the dependent variable along the y axis. But what is an independent variable and what is a dependent variable? How do we decide that which quantity is independent variable and which quantity is dependent variable? Let us see, it depends upon the situation. Here I have drawn data from a certain experiment which was done, where we found the speed of sound in a certain material as a function of temperature. You can see the temperature is increasing and the speed of sound is also increasing along with it. And in this case, the change in the speed of sound is a consequence of the change in temperature. Therefore, we designate temperature as independent variable and the speed of sound as dependent variable. But remember, the temperature is not always an independent variable. As I said, it depends upon the situation. For example, if we were considering the rise in temperature of a liquid as it is heated, then the temperature would become a dependent variable. The time for which the liquid is heated would then become independent variable. So, dependent variable and independent variable, they all depend upon the situation which we have at that time. Now, points to consider while drawing a graph. First, identify independent and dependent variables very clearly. Then choose scales so that the graph fills most of the available space. Scales must be convenient for plotting the points on the graph, and they must be mentioned clearly on the graph itself. Remember that larger the graph that you can draw in the given space, easier it is to interpret it. Let us draw a graph and illustrate these points. I have here a data from the journey of a bus. You see that in the first column we have time, say 8:30 a.m., 9 a.m. and 9:30 a.m. and so on, and the last column we have distance from the starting point, 0 kilometer at 8 o'clock, 20 kilometer at 8:30 and so on. And we now draw a graph point by point. See that on the y axis we have taken distance, which is in this case a dependent variable. On the x axis we have taken time, which is in this case an independent variable, and we draw each point, first point, second point in that data, third point, fourth point in that data and fifth point, and ultimately we join all these points by a line. This line is the graph between distance and time. And what is the use of this graph? You can see that if we need to know when the bus had covered a distance of, let us say, 10 kilometers, what time at that time was there on the clock, and you can see the time would be given by this point. Similarly, we shall see when the bus was 70 kilometers away, what time was it? Again we draw a perpendicular line and read the time on the time axis. We can also extrapolate, we can find out where would the bus be at 11 o'clock. and we find that this would be at about 120 kilometers. So, the graph serves many purposes. It tells us the speed, it tells us where the bus was at a certain time or what distance it had covered at a certain time, and so on. Now, we are ready to consider motion in one dimension. In one dimension, since we have only one line along which the body goes, there is no need to distinguish between the distance covered and the displacement. Therefore, we shall now take distance time graph rather than displacement time graph. And if we take distance time graph, then the velocity would be constant if the graph is linear, and it would be variable if the graph is non-linear. And we draw various graphs for you to show the position of a certain body. Here the body is at rest. You can see the distance is not changing with time. Here the body is moving away from us with a uniform speed. Here the body is coming towards us. You can see the slope is negative, therefore, the speed is negative, velocity is negative, it is coming towards us. Here it is again moving away, but this slope is larger than the earlier slope along this line, and therefore, the speed is higher. And lastly, we will show the speed is increasing in the graph with this red line. If we can read the various slopes at various times, then we can say whether the speed is increasing or decreasing. In this case, this blue line is uniform speed, where this red and dark line, they are showing the speed is increasing. On the dark line, of course, it is increasing faster because the slope is increasing. Let us repeat again distance time graph. The slope of this graph shows us the velocity. Now, if we have velocity time graph, then the slope of this graph would show us acceleration. Why? Because velocity by time is acceleration. Therefore, if we have velocity time graph, then its slope would be acceleration, and if the graph is uniform or linear, that means the acceleration is uniform. And most of the time we deal with uniform acceleration earlier classes. Now, I will show you how to draw various graphs. If you have distance time graph, how you can get from this the velocity time graph. In this case, you look at this graph, the upper graph, it is distance time graph, and you can see the body is moving away, then it is at rest, then it is moving back, but faster. What would be the velocity time graph like? Velocity initially is constant, then the velocity becomes 0, and then the velocity becomes negative with a larger magnitude than the earlier velocity. So, from distance time graph, we have arrived at velocity time graph. In this slide, we have velocity time graph which we obtained in the previous slide, and you can see that if velocity is constant, then acceleration is 0. Velocity is constant here, but negative, but acceleration is 0, except at times t1 and t2. At time t1, the velocity reduces from some positive quantity to 0, that means there is an acceleration. At time t2 also, the velocity goes from 0 to some negative value, and again there is some acceleration. So, from velocity time graph, you can get the acceleration time graph. Here I show you various samples. You have distance time graph, the velocity is constant and acceleration is 0. Here the distance time graph, the velocity is decreasing, distance is decreasing, velocity is constant but negative, and acceleration is constant. Here the distance is increasing and then decreasing, the velocity is changing from some value to 0 and then from 0 to negative values. The acceleration is constant throughout. Here distance increases from some negative value and then it increases non-uniformly. The velocity here is constant and here it varies, and acceleration, since the velocity is constant, acceleration is 0 and acceleration is constant in this segment, and in between there is a change in the acceleration because of the change in velocity. Here distance is decreasing and again increasing, velocity is negative but uniform, In this segment, velocity is constant and positive. Acceleration, of course, appears only when there is a change in velocity, at this point only, because there is a change in velocity only at this point from negative to positive. Here is just the opposite, distance increasing, velocity constant, distance decreasing, velocity constant, but negative, and acceleration appears only when the velocity changes from positive to negative. Now, given a velocity time graph, how do we find the distance covered? If the velocity is constant, then it is easy. Between time t1 and t2, the distance covered is v into t2 minus t1. So, there is no problem. But if the velocity is changing uniformly, let us say, then how do you find the distance covered? For this purpose, we do this. We draw strips, very narrow strips on this graph, just like here, and for this narrow strip we can assume the velocity to be uniform, and therefore, the distance covered is the area of this strip, and we can erect many more strips of this kind, and you can see here one, another, and if we cover all this area by these strips, then the total area would be equal to the area of these strips. That means, the total area would be equal to the distance covered, as we have shown here by covering this triangle by this mesh. So, the distance covered is equal to the area of this triangle. In general, the distance covered is equal to the area under the velocity time graph. If we have a graph, then the up to time t, the distance covered is given by the area of this triangle. And what is the area of this triangle? This distance p q is equal to a t. Remember, a is the slope of this graph. A acceleration is the slope of velocity time graph. Therefore, a is the slope, and therefore, this distance p q is a times t, and therefore, the area of this triangle is t into a t divided by half. So, it is half a t square. Now, suppose the body started with a uniform initial velocity u, then the distance covered would be equal to this rectangle and this, the area of this triangle, which is u t plus half a t square, because the body started with initial velocity u. Therefore, we draw this rectangle and draw this triangle and take the area of these two, and we get the formula that the distance covered is equal to u t plus half a t square. If the velocity is changing like this, then we again take the same route. We draw strips, cover the whole area, and then we find that the distance covered is equal to area under this curve from time t1 to time t2. That is, velocity has this shape, we draw strips, cover the whole area, and we know the area of each strip is given by v into t. So, therefore, the whole area would be equal to the area of these strips, which is the area under this curve from time t1 to t2. So, the distance covered from time t1 to t2 is the area under the velocity time curve bounded by the ordinates at t1 and t2. In this lecture, we have seen the relationship between distance time graph, velocity time graph, and acceleration time graph, and we have seen how from distance time graph we can get velocity time graph, and from velocity time graph we can get acceleration time graph. We have also seen how we can get the distance covered from certain time t1 to certain time t2. We have seen that this distance covered is equal to the area under the curve. In the next lecture, we shall deal with kinematic equations. Some of these equations we have derived here, we shall derive them again and then see how we can deal with problems involving kinematic equations.